Hi, I'm going to talk about cross product. This is section 12.4 in the Stewart textbook. This is the second way to multiply vectors. We talked about dot product, and we know that if you take the dot product of two vectors, the result is a scalar. And now here we have cross product, which is a second way to multiply vectors, and we're going to learn about that. To talk about cross product, we have to start with determinants. So let me explain what a determinant is. A determinant of a matrix is a certain formula. So start with a 2 by 2 determinant. If I have a 2 by 2 matrix, that means a 2 by 2 array of numbers. The determinant of it is just these two multiplied, a times d, minus those two multiplied, b times c. So AD minus BC. That's the determinant. And I can use, you see how there's some 2 by 2 determinants written here? I can use those 2 by 2 determinants to do a 3 by 3 determinant. If I have a 3 by 3 matrix, that means a 3 by 3 array of numbers. Then I can get the determinant of that 3 by 3 matrix. Well, this is a pretty big, crazy formula, but it breaks down. Look what's going on here. I'm highlighting an A, whatever the entry is in this spot, the number that's in that spot, and then if you cross out the row and column of that A, so cross out that row and cross out the column, and what's left over, I've highlighted it in blue, EFHI, and that's that 2 by 2 determinant. That we just saw right before this, how to do a 2 by 2 determinant. And then after A, I'm highlighting the B. And again, if we cross out the row of that B and cross out the column, then what's left over is this DFGI thing. And there's that 2 by 2 determinant of a DFGI. The only tricky thing is notice this minus sign. Tricky minus sign. And first I did A, then I did B, and you can see where we're going next. We're going here to C. And there it is. There's the C that's highlighted. If I crossed out the row of the C and the column of the C, then what's left over would be this DEGH, and there's that 2 by 2 determinant of a DEGH. So you use the 2 by 2 determinant to build up to a 3 by 3 determinant. This determinant formula is pretty crazy. It's true. Let's do an example with numbers. So let's do the determinant of 275, 175, and 170. And if you want to try it yourself, you can just pause the video and try it and see if you get minus 35 as your answer. But let's go through it together step by step. So I'm going to go across the first row, my ABC row, where the 275 is. So I'm highlighting the 2, and remember what we do is we cross out the row and column of that 2 and see what's left over. 7570, put that in a 2 by 2 matrix. Then we move to one step sideways to the 7, cross out the row and column of that 7, it's sort of a T-shaped kind of deal. And what's left over is 1510, put that in a 2 by 2 matrix. Only thing is, remember the minus sign. That's kind of tricky and easy to forget. If you haven't done this before, it's easy to forget. So just remember. And then to finish, going across the top row, I did the 2, I did the 7, last one is the 5. So here's our 5. And cross out the row and column, and look what's left over, 1, 7, 1, 7. Put that into a 2x2 matrix. All right, so I've got my 3x3 determinant broken down into 1, 2, 3 pieces, and each piece is a 2x2 determinant, which, good news, the 2x2 determinant wasn't that complicated. We can figure that out. If you want to pause the video and just do that step yourself, this 2x2 determinant is multiply those entries, that's called the main diagonal, 7 times 0, and then subtract the opposite diagonal, 7 times 5. Come to this 2x2 determinant, multiply the main diagonal, 1 times 0, subtract the opposite diagonal, 1 times 5. And then in our last matrix, we multiply the main diagonal, 1 times 7, and then subtract the opposite diagonal, 7 times 1. So work out those numbers. We've got 0 minus 35, 0 minus 5, and then 7 minus 7. So 2 times minus 35, minus 7 times negative 5, and then plus 5 times 0. So there's 35 times minus 2, and another 35 gets added on. And the end result is minus 35 after you do a bunch of arithmetic. All right, that's how we compute determinants. I want to show you how to use determinants to do cross products. Sometimes determinants are useful for other things. If you've taken linear algebra or differential equations, or if you're going to take those in the future, then you see some other uses of determinants. And if you've taken those classes, then and if you've taken those classes and you learned determinants before, then you might have learned some other ways to compute determinant besides the way I've shown it. Those are valid. They're completely allowed, and I am 100% okay with it. You can compute determinants any way you want. However, I do need you to make sure, even if you have another determinant method that you like, that's fine, but I need you to learn this top row method. It's kind of important, and you'll see why for cross products. Kind of have to use the top row method, and later on we're going to do other stuff with curls of vector fields where you even more so have to do the top row method. But if you want to compute determinants another way, you can do that. Just make sure that you have this ability in your repertoire. Okay, you know what? If you haven't done determinants before, if this is the first time you're seeing it, it's real simple. Do it the way I showed it. Don't worry about other methods. You can learn those in other classes later. All right, so we got determinants, and here's how it ties in with with cross products. Unlike dot products, where it could be any dimension, dot products could be any dimension as long as the two vectors were the same number of dimensions as each other. Cross products is a little bit different. It's got to be R3. We're only going to talk about R3. So not R2. Not R4. Or any other number of dimensions. I almost misspelled dimensions. Ooh. Any other number of dimensions. Okay, only R3. There are sort of cross-producty things in other dimensions, but it's a whole other story, and I'm not going to get into it right now. maybe later, or if you ask me about it, I'll tell you. But we're going to focus on cross product here. So here's what the cross product is. The cross product of V cross W is given by a determinant. It's a 3 by 3 determinant, so you can see why we needed to look at 3 by 3 determinants. And it's a 3 by 3 determinant where I take the first vector in my cross product, which is V, and I list it across that row. And then I take the second vector in my cross product W, and I list it in that row. But even before I did that, I put ijk on top. And now, here's the kind of weird thing. I was talking about determinants of matrices that had numbers in them, right? In our example, it had numbers. Like it had 2, 7, 5, those are numbers. And wait, ijk are not numbers, they are vectors. So that's kind of weird. So I'll show an example to show you how that works. But one thing you can see is that this formula is a formula that has vectors in it. We're going to be multiplying and adding together vectors. And so the result is going to be a vector. The cross product of two vectors is going to be a vector output. All right, let's see an example. So here's an example fully worked out, and I'll just sort of talk through it. So I've got 2, 7, 5, cross product 2, 0, 20. So I set up my 3 by 3 matrix. I put ijk on top, and I put my first vector as the row under that, ijk 2, 7, 5, and then I put my second vector 2, 0, 20 as the next row under that. And I've got a 3 by 3 matrix, and I would like to know the determinant of it. Okay, using our rule of going across the top row, the ijk row, what I do is I start with the I put that I there, and I cross out that row and column, and what's left over, 7, 5, 0, 20, goes into this 2 by 2 matrix. Then I move from the I to the J. I put a J there. I cross out the row and column, that sort of T-shaped thing. And look at what's left over. I've got a 2, 5, 2, 20. 2, 5, 2, 20. I put those there. And remember that tricky minus sign. Okay, so that's our J. And then we move on to the K. And you can see I've got a K here. So then I cross out the row and column of this K and see what's left over. There's a 2, 7, 2, 0. And there it is, 2, 7, 2, 0. Now we have to work out all the 2 by... So that was the hard part, right? That was the 3 by 3 determinant is the hard part. But once we've done that, now I've got a 2 by 2 determinant, 7, 5, 0, 20. So that's 7 times 20, 140 minus 0. In this one, I've got 2 times 20 minus 2 times 5. So it would be 40 minus 10. And in our last matrix with the K, I'm doing 2 times 0, main diagonal, minus 7 times 2, the opposite diagonal. So 0 minus 14. And those are the results we're getting. I've got 140. That gets multiplied by I. 30 gets multiplied by j, but there's a minus, so I end up with minus 30j. And then minus 14 gets multiplied with k, minus 14k. So first I wrote it with IJK notation, and that's valid. That would get full credit. And then I rewrote it using angle bracket notation. That's also valid and would get full credit. I really don't have a preference. If you have a personal preference which way you write it, go for it. That's fine. I'm neutral. Sometimes on WebAssign, it needs to be written one way or the other, so you have to pay attention to that in WebAssign if they are requiring a format. But if no one's requiring a format, then whatever, just use whichever one you like. Okay, so in contrast with dot product, in dot product, if you put your dot product entries into a vector, that's a big mistake and you forgot to add them up. But in cross product, you are supposed to put your entries into a vector. We are supposed to put our 140, minus 30, and minus 14 as entries in a vector. We're not supposed to add them up. So that's the difference with the dot product versus cross product. Here's a question for you to practice one. So I'll go through this in just a minute, but you might want to pause the video and try working it out yourself. Cross product of 111 with 123. So you can pause the video and try. Okay, 111 cross product 123 is the determinant of a 3x3 matrix where I put I, J, K on top. Then I put my first vector. Then I put my second vector as the second row. Okay, so I've got an I. If I cross out the row and column of that I, what's left over is 1, 1, 2, 3. Minus J. If I cross out the row and column of that J, that sort of T-shaped thing, what's left over is a 1, 1, 1, 3, and never have enough room. Gonna come down on the next line for the K. If I cross out the row and column of K, what's left over is 1, 1, 1, 2. All right, let's figure out these 2 by 2 determinants. Here I've got a 3 minus 2. For this J, I've got main diagonal 3 and opposite diagonal 1. And for the K, main diagonal 2, opposite diagonal 1. So it's I times 1 minus J times 2 plus K times 1. And if you wrote it sort of normal, it would be like I minus 2J plus K. And, all the answers are written with angle brackets. So I guess we should write our answer with angle brackets. And then when it's written that way, you can match it up. Looks like this matches with A. Looks like A is our answer. Yep, the slides confirm it. All right. What are some geometric and algebraic properties of cross product? I guess we're starting with geometric properties. So the 3 geometric properties that are written here. First of all, the cross product V cross W is orthogonal to both V and W. It's orthogonal to V and it's orthogonal to W. It's orthogonal to both of them. We can check that in our example. We did 2, 7, 5 cross product another vector, and the result we got was this vector here. Like this was our V, and this was our V cross W. And we can check if they're orthogonal. If you remember how to check orthogonality, you can check orthogonality by doing the dot product, and we hope we get 0. If we check, we got 2 times 140 makes 280. 7 times minus 30 makes minus 210. And 5 times minus 14 makes minus 70. And when we total those, 280 minus 210 minus 70, we get 0. So, yep, they are orthogonal. So that confirms it for that example. And what I'm telling you is it's not just that example. That's in general. Any vectors. And I'm going to cut over to a camera and show you with my hands. But that kind of narrows down the directions, right? Like V and W are pointing in certain directions. And being orthogonal to both of them kind of narrows down the direction that the cross product can be in. So I'll demo that in real life. Okay, so what does it mean if I say that a vector is orthogonal to both V and W? So here I have a couple of vectors. Let's say this one is V and this one is W. So what could be orthogonal to both of them? Well, the way it's set up, this could be orthogonal to both of them. This is at a right angle to both of them. It also could be this way. But we've narrowed it down. Saying that it's orthogonal to both of these vectors sort of forces it to be along this line through here, through the long direction of this sort of blue football-shaped thing. And we'll see in a minute which way it goes. Is it up or is it down? But right now, the orthogonality means that we're somewhere along this line. So we've narrowed it down to that. Okay, so that kind of narrows down the possible directions of V cross W. What about the magnitude? Well, according to this rule that's written here, the magnitude of V cross W is magnitude of V times magnitude of W times sine of theta, where theta is the angle between those vectors. It's the same theta that we were talking about with dot product. And dot product had a cosine theta. Cross product has a sine theta. If you want to be a little bit technical about it, it's absolute value of sine theta, which for various reasons usually doesn't end up mattering all that much. But if you want to be careful, if you want to be technical, it's in there. And, you know, can sort of digress a little bit and tell a terrible joke. So this is the joke about cross products, where the magnitude of V cross W is the magnitude of V times the magnitude of W times sine theta, where theta is the angle between them. And so the joke is, what do you get if you cross an elephant and a mouse? And the answer is elephant, mouse, sine theta. But then the second joke is, what do you get if you cross an elephant and a mountain climber? And the answer is not elephant, mountain climber, sine theta. The answer is you can't cross an elephant and a mountain climber because a mountain climber is a scalar. And so now, how much of the geometric properties do we know at this point? Well, we know the magnitude of our vector. Do we know the direction? If you think about it, we almost know the direction. We know the line that V cross W is on, but we don't know which way it's pointing on that line. It could be sort of pointing one way or the other way. It could be flipped. And there's this right-hand rule to tell us which direction it's pointing in. And so let me talk through the right-hand rule on the slide, and then I'll cut over to camera to show you how it works in real life. The right-hand rule is that these vectors form a right-hand system. So if you point your right-hand fingers along the first vector, V, and you curl them, so you have your hand flat. You have like a flat hand, like you're going to high five somebody with your right hand fingers pointing along V. And if you curl your fingers so that now when they're bent, they're pointing along W. If you do that, your right hand thumb is pointing along V cross W. Sometimes people use other versions of the right hand rule, like using their palm. Like, for instance, maybe you have a flat, like a high five hand, and you point your right hand fingers along V, and you make your palm face towards W, the palm of your hand face towards W, then your thumb is pointing along V cross W. Or people have other variations. That's fine. You know, if you learned a different version in physics or whatever, fine, whatever. This is just one option that works. Now I'd like to show the right hand rule with my right hand. There's more than one way to do this. Here's how I explain the right hand rule. I point my fingers, my right hand fingers, along the first vector, and then I curl them so that they point along the direction of the second vector. And at that point, my thumb, my right hand thumb, is pointing in the direction of the third vector. So if this was V and W, then V cross W would be pointing in that direction. If V and W were this way, like say this one was V and that one was W, then I would point my right hand fingers along V and curl them so they're pointing to W, and then my right hand thumb is pointing in the direction of V, and so V cross W, pointing in the direction of V cross W would be pointing here, this way. V cross W, thumb pointing towards V cross W. So here's a question for you to see how much that right hand rule makes sense. Say that V points along the positive Z axis and W is in the XY plane, but it's in the first quadrant, meaning the X is positive, Y is positive. If we do the cross product V cross W and look at the vector components of it, are those components positive, negative, or zero? Are they positive, positive, negative, negative, positive, zero, zero, minus, minus, or minus, zero, minus? So think about that, pause the video and get out your right hand and give it a try. So do V cross W, cross product. What do you get? Well, if you pointed your right hand fingers in the positive Z direction and then curled them down to point along W, then your thumb would be pointing this way in the XY plane. And it would be at a right angle to W. So in that part of the XY plane, between the positive y-axis and the negative x-axis, that's where V cross W would end up. So if it's in the XY plane, in that part of the XY plane, that means that the X component is negative, the Y component is positive, and the Z component is 0. So our answer is that the X component is negative, the Y component is positive, and the Z component is 0. And looking at that answer, that matches up with B. We're going to stick to right-handed coordinate systems. This is something that also comes up in physics sometimes, in some situations, meaning that the X, Y, and Z axes should work with the right-hand rule. So if you point the fingers of your right hand in the X direction and curl them towards the Y direction, then your thumb should be pointing in the Z direction. If you try that with B, then my thumb is pointing up. If I tried that with A, I'd have my fingers pointing in the X direction, curl them to the Y direction, my thumb would be pointing down instead of up. So A shows Z pointing up, but my thumb ends up pointing down. So A is not right-handed, it is left-handed, but B is right-handed. All right, so those were some geometric properties and right-hand rule, and now I'm switching over to talk about algebraic properties. So the big warning about cross product is that it is not associative. You cannot move the parentheses like that. U cross V cross W, you will get a different answer if you do U cross V and then cross with W versus if you do the V cross W and then cross U onto that. And for that matter, it's also not commutative. U cross V and V cross U do not give you the same answer. They are not equal. They're opposites. They're minus of each other. Commutative is like U dot V equals V dot U. But these cross products, they're not equal. Instead, there's a minus sign. They are distributive. U cross V1 plus V2, it does distribute U cross V1 plus U cross V2. It does have distributive, and it has left and right distributive properties. The V being on the right does distribute onto the U2 and onto the U1. The V gets crossed onto the U1, the V gets crossed onto the U2. So it does have distributive property, but not commutative property. What if you cross a vector with itself? I mean, dotting a vector with itself was kind of interesting, right? Do you remember what happened when we dotted a vector with itself? We got the magnitude. What happens if you cross a vector with itself? Well, you end up with 0. Why do we end up with 0? It's because of that formula. U cross U, the magnitude is the magnitude of U times the magnitude of the second vector, which is also U, times sine of the angle between them. Okay, what's the angle between a vector and itself? It's just 0, right? Because it's like U versus itself, 0 angle between them. And what's sine of 0? Sine of 0 is 0. So I'm getting magnitude of U times itself times 0. Just get 0. So this U cross U vector has length 0. And that's why U cross U is 0. I guess technically this should have been a 0 vector. Well, I left out the vector symbol on my 0. And one more property that is sometimes kind of handy, I cross J equals K. If you think about it, that's basically what we were saying on the previous slide about right-handed systems. We said that the x-axis crossed with the y-axis. If you did the right-hand rule with your fingers and curl them from the x-axis to the y-axis, then your thumb would point in the z-axis direction. So that's just like saying I cross j. It's the same right-hand rule, and you should go into the positive z direction. That's k. But now getting beyond that, that was our right-handed system. So getting a little bit beyond that, we're also saying that j cross k is I, and k cross I is j. And you're supposed to notice a kind of pattern here, like I've got a column of i's, j's, k's, and then I, j, k, I, j, k. So sort of an I, j, k pattern. Like if I kept going, I cross j would be k again, and then j cross k would be I again. And you could sort of imagine keeping going like that, and you'd have a column of i's, j's, k's, I, j, k, I, j, k forever, right? And our equation is just sort of shifting down, shifting one spot. It's an ijk equation, and then it moves over one spot to be a jki equation, and then it moves over one spot to be a kij equation, and then it moves over one spot to be an ijk equation. It's the same ijk equation as before, so that's why we don't really need to repeat it. Yeah, we don't really need to repeat it, right? But I just wanted to show the sort of repeating pattern. And sometimes that comes in handy. Like, if somebody says, oh, find the cross product of 1, 1, 1 with 1, 2, 3, then, you might as well just use the determinants. But if, hypothetically, somebody would say, can you please find the cross product of j cross k or something, or like, j cross j plus k, something simple like that, then sometimes these simple rules are kind of handy. Oh, look at that, a hypothetical situation where somebody gave you some i's and j's to cross product. So what is the cross product of 2i cross 3j? Is it 6k minus 6k, 0, or 6ij? It is 6k, right? It's 6k is our answer. Because one of the properties of cross products that apparently I forgot to mention, I'm sorry, is that you can pull the scalar out in front. And then we could pull the other scalar in front. And I guess 2 times 3 is 6. And then we know a rule that I cross j is k. So our answer is A, 6k. This student just made a mix-up and they put a minus sign by accident. This student, well, I don't know what they were thinking. It's not 0. They might have been thinking dot product. If I dot producted 2i dot 3j, that would be 200 dot 030. And for a dot product, I would get 2 times 0 plus 0 times 3 plus 0 times 0. So we get 0 plus 0 plus 0. It would be 0. So maybe that student did a dot product. Accidentally did a dot product. Instead of cross product. Oops. And then this student just multiplied 2i times 3j and they got 6ij. No, don't do that. cross product, closing thoughts on cross product, some tie-ins with area and volume. This is a parallelogram. It's sort of a tilted rectangle. So just a reminder, the area of a parallelogram, the area of this shaded parallelogram, turns out to be the base times height. The base times height. Just like a rectangle. I mean, the difference with a rectangle is that this isn't the height of the parallelogram, right? That's the difference with a rectangle. In a rectangle, the height is the same thing as one side. But in this parallelogram, what's going on? Well, the base is V, or magnitude of V. The base B is the magnitude of V. And what about the height? According to trigonometry, we got a right triangle here with angle theta. And according to trig, this h is the hypotenuse times sine theta. H is magnitude of W times sine theta. So the upshot is that this is something we've seen before. Do you remember where we've seen it before? We saw it before for the magnitude of the cross product. And now we're seeing it again for the area of a parallelogram. So the area of a parallelogram made by two vectors turns out to be the magnitude of the cross product. So sometimes that actually works out as a good way to find area. Like, you got your two vectors, so you have to go through some steps to do it, right? Like, you have to go through that 3x3 determinant, and then after that, then you have to find a magnitude. So it's got some steps, but still, sometimes that's useful. And then there's also a tie-in with volume. And I'll skip ahead to that slide and then come back. The volume. So we're going to figure out the volume of this parallelepiped, which, you know, if you're a normal person, you'd use an easier word than that. Like, man, if you're really enthusiastic about this, parallelepiped, but maybe you call it a skew box or a prism or something. This is a box where the opposite sides are parallel. So the top is parallel to the bottom. The front is parallel to the back. And the side is parallel to the side. And it's a skew box. It's a sort of tilted box. Just like how a parallelogram was a tilted rectangle. So this is a tilted box, or skewed box. So if the edges were U, V, and W, the edges coming out of one point were U, V, and W, then the volume of this would be given by a certain formula. It's this thing that's explained on the previous slide called the triple product. The triple product is of UVW, it's taking a cross product V cross W and then dotting that with U. So you can see why it's called a triple product, because it takes 1, 2, 3 vectors. Turns out it's the same thing if you cross the first 2 vectors and then dotted it with the last one, as it turns out. Maybe not super obvious. One thing that we can check is this triple product U dot V cross W. It's the same as what we would get if I did a determinant with U in the first row, V in the second row, and W in the third row. And just for funsies, we can take a minute and see why that's true. If I had U1, U2, U3 in the top row, if I did my top row rule for determinant, I would have U1, U2, U3. And then when I cross out the row and the column of the U1, what's left over is the VW in the second, third columns. If I cross out the row and column of U2, what's left over is V and W in the 1 and 3 columns. If I cross out the row and column of U3, what's left over is V and W in the 1 and 2 columns, because I crossed out the third column. And now here's a neat little trick. Anytime I've got a bunch of things, here's a thing, a second thing, and a third thing added together, but they're multiplied and added together, I can reverse that into being a dot product. If you listen to the lecture before this, you might be thinking of a dot product as like, to dot 2 vectors, you make it into you multiply and add up. Here I've got multiplied and add up, and I'm going to reverse that into being a dot product. A U1, U2, U3 dot product with, well, a kind of crazy vector, which is a determinant minus this other determinant, and then the third determinant. So that's U, and it's being dotted with this kind of crazy vector. And so now I'm going to kind of skip a step, but if you write this out, that crazy vector is just V cross W, just written out. So that's U dot V cross W. And that's what I was saying, is that this 3x3 determinant is the same thing as U dot V cross W. Okay, well, I mean, for me, it's kind of fun to explain why things are true and how we know. And I hope that it's fun for you too, to kind of understand and learn and to think about conceptually why are things true and how does it work and how do we figure these things out. And that's part of what college is about, is about going beyond just learning a method to find the answer, right? It's like, how do you think about it and how do you understand it and how do we know that it works? Why does it work? So I hope that you see some value in that, and I hope that you enjoy it. But to tell you the truth, in this semester in Math 275, it's kind of secondary. The primary thing is just understanding how to do cross products. So if you wanted to focus on the most important thing, this proof of why that equation works is maybe not the most important thing. The most important thing is just a triple product is for 3 vectors U, V, W, do cross product 2 of them and then dot it with the other one. And the reason why it matters is because of this next slide that we kind of already started to see. This volume is given by that triple product. And I just went through the reasoning for why that gives you the same answer as a determinant. Now, if you want to ask me why, so this equation, like these two being equal, we talked about why these two are equal. If you want to ask me why this equation, why the volume is given by that, well, that's a little bit beyond today's topic. That's going to be a story for another day. It's a true statement. I'm not telling you lies. It's not beyond our comprehension or anything. We could do it, but I think I've said enough, and I'm just going to leave it there for now and worry about that some other time. Okay, so we'll use the parallelogram area sometimes, and we'll also use this box volume sometimes. So you'll see how these are useful things for us later on as we go through some calculus things. And that's the cross product. Maybe a closing thought. We've got two different ways to multiply vectors. I give you a vectors u and v, and I say, oh, what do you get if we do the product of those vectors, u and v? Well, you should ask which kind of product. Do you want u dot v or u cross v? U dot v versus u cross v. The dot product gives you a scalar result. The cross product gives you a vector result. The dot product can be in any number of dimensions. Like these could be vectors in R2 or R4 or whatever. The cross product, they have to be vectors in R3 to talk about it. So one upshot is that, like, for numbers, if I did 2 times 3 with a dot or 2 times 3 with a times sign, you get 6. They're the same. The times signs are the same for numbers, but not the same for vectors. So therefore, please pay attention to whether it's a dot or a cross. And when it comes to vectors, you cannot just switch them around. Like with numbers you can, with vectors you can't. They're not the same.